Welcome to this video in which we will demonstrate how to do ad hoc circuit analysis with a circuit that has a dependent source. The circuit that we will analyze will be a small signal model for a MOSFET amplifier. The MOSFET amplifier circuit is shown on the left here, and the MOSFET itself is a solid-state device that can be used as an amplifier. The idea is that you take this MOSFET, which is a nonlinear device, and you do what's called biasing. So you set the voltages and currents on the MOSFET so that it's operating in what's called its linear range. And within the linear range, you can then look at differences between the nominal operating point and the actual currents and voltages in the MOSFET. And these differences are called small signals. And what you typically do then is use the MOSFET to amplify the small signals. There are ways of making that work where you're using coupling capacitors or other sorts of methods of coupling signals together, which are quite a bit beyond the scope of this video. So on the right here we have our small signal model. And this is a circuit that we'll actually analyze. In this circuit, the part that I'm outlining in green, this is actually kind of a dumb way to do it, but this represents the MOSFET. And the reason I go right through the middle of this 2 k ohm resistor is that this 2 k ohm resistor represents both an internal resistance in the MOSFET and this R sub S. This is called a common source amplifier, and it turns out that it's, as you'll see, the voltage out is very similar to the voltage in, but it allows you to decouple amplifier stages. So if that whole discussion of MOSFET amplifiers seemed pointless to you, hang on, because the part that this is really designed to show is how to do ad hoc analysis of a circuit with a voltage-controlled current source in this case. You'll notice that I have a dependent current source, and that current source is controlled by this value. So the source looks at the voltage VGS, which is the voltage from this point to this point, multiplies it by 30, and that's the value of the current that the source provides. So let's figure out then how to do the analysis. This one's going to be a bit tricky because we will need to actually use one unknown here, unlike simpler ad hoc analyses where you can basically just work your way through the circuit. In this case, we're going to have the unknown of VGS, and then as we go through the circuit, we'll come up with an equation that VGS has to satisfy, and then we'll solve that. Okay, so let's begin then. If we assume that we knew VGS, which again we don't, so if we assume that this were known to us, then we know that the current flowing through the source is 30 VGS. And you'll notice that this current flows around in this loop. You may ask, well, why don't I get any current that flows like this or like this? And the answer is that there is an open circuit right here, and current cannot flow through an open circuit. And since current has to flow through a loop, there's no way for current to take this branch and end up going back into the current source. There just can't be done. And similarly, if I try to go the opposite direction, I just can't do it. So basically what I know is that all of the current that flows through this dependent source flows around this loop through this 2 k ohm resistor. So this tells me then that the current, which again is 30 times VGS, times the resistance, 2 k ohms, is equal to my output voltage. So this is good. This is useful information. Again, my goal is eventually to solve for the output voltage. But I still have this unknown voltage here. So I need to figure out an expression for VGS. Once I do that, then I'll be able to solve for VGS and then solve for Vout, and we'll be done. Okay, so to do that, to solve for VGS, I will take a loop that goes around the circuit like this and apply Kirchhoff's voltage law. Okay. Now I guess I'll do it both ways, or I'll do it explicitly and then do it implicitly. So I have VGS going from here to here plus Vout minus 3 volts is equal to 0. That's basically just going around this loop as I encounter voltages. From plus to minus, they show up with a positive sign. From minus to plus, they show up with a negative sign. Another way of looking at it is the voltage from this point to this point is set by the 3 volt source to be 3 volts. So that means that the voltage VGS from here to here plus the voltage from here to here, V0, would be equal to 3 volts. So if I do the more informal analysis, I get this, which is mathematically equivalent to this. Okay, so I have 2 equations and 2 unknowns, and it looks to me then like we can probably solve for VGS and then V0. We could actually solve directly for V0, but I'd actually also like to know what VGS is. So I have this expression for V0, or I have V0 is equal to this whole expression. I can plug that into my VGS plus V0 equals 3 volts and get the following. I have VGS plus 30 VGS times 2K ohms is equal to 3 volts. Now I can simplify this. I have 30 times 2K ohms. That's basically 30 times 2,000, which is 60,000, 6 times 10 to the 4th. Okay, so I can then simplify this. I can factor out this VGS. In fact, let's do this now in a different color. I can factor this VGS and this VGS out. So I have VGS 1, that's the coefficient in front of this guy, plus 6 times 10 to the 4th is equal to 3 volts. Or you can see then that I can solve for VGS. VGS is equal to 3 volts divided by 1 plus 6 times 10 to the 4th. And I can work this out. And I'm going to get something that's very, very close to 0. But let's see how close it is to 0. We have 3 volts divided by 1 plus and I get that this is 4.99917 times 10 to the minus 5th. Now normally I wouldn't keep this many significant figures, but it turns out in this case, in order to get V out being anything other than 3 volts, I need to have it be this, carry out this many significant figures. So now let's clear out a bit of space. We can go back to this equation, this guy right here, and find V out. We have V out is 6 times 10 to the 4th, That's what we decided this guy times this guy is, times VGS. And if I work this out, I get that V out is equal to 2.99995 volts. Okay, so what we found then is that this voltage here is 2.99995 volts. It's almost exactly the same as this 3 volts. The only thing that makes it different is I have this 1 down here that gets added to the 6 times 10 to the 4th. So it turns out this is a circuit that's often called a voltage follower, in the sense that the output is almost the same as the input, but it has useful properties in the sense that it allows me to decouple something over here from something over here electrically. Again, that's a topic that's much more advanced than we'll do in this video. The purpose of this video, again, was to show an example of working or analyzing a circuit that has a dependent current source. So, thanks for watching. I hope it was useful.